Well, in the last couple of classes, you have learned analog, and therefore we form no mental picture of it. We just take it at its face value that it has a two-valued character. Even though the Stern-Gerlach apparatus does not allow us to get the exact value of that, but from various other considerations, we have understood that it has two values, which are plus minus h cross, sorry, h cross by 2. So the value actually we know, at least for the particle that we're considering. You might ask, we are doing the experiment with silver atoms. Why silver atoms? We could have done the experiment with electrons. We could not do that, or Stern and Gerlach could not do that, because electrons are charged particles. If something is a charged particle, then they are automatically deflected, and if they're moving, they will automatically deflected by a magnetic field. And so the deflection, because of their charged character, will be far greater than the tiny deflection that happens because of the non-uniform magnetic field because of the spin. So the actual effect that you want to study will be swamped by another effect. That's why we do not use electrons to do this experiment. But then why silver? The silver has a property that there are many electrons going around the nucleus, and the orbital angular momentum of almost all of them cancel off each other. No, actually all of them cancel with each other. So actually the whole atom does not have any orbital angular momentum. The spin angular momentum of most of the electrons cancel with each other, leaving only one. So effectively, by measuring the character of the silver atom, we actually measure the angular momentum character of a single electron. That's a major advantage, and the atom itself is uncharged, so it doesn't get deflected by because it is or had it been charged, then it would be deflected by the magnetic field. So that effect is none.
So, could you please repeat why we choose silver atoms?
Yeah, the silver atom was chosen because, I mean, when Stern and Gerlach did that experiment, they probably did not have an idea why silver. I mean, they just chose an atom because at that time the actual character of the angular moment and things like that were not known. They did the experiment in 22. That it was fortuitous that they chose silver, but now we know that had they chosen, say, sodium or magnesium, it would have the same effect because they also have the same character. The character is that there are many, silver is has many electrons in it, and each electron will have angular momentum, orbital angular momentum. But they're oriented in such a way that their orbital angular momentums cancel off. So there is no net orbital angular momentum. But there is one electron whose spin is not cancelled off. Spin angular momentum is not cancelled off by the others. So for the others, the net spin angular momentum also cancelled off, leaving only one electron whose spin is actually not cancelled off, and therefore the whole atom carries the spin of one single electron. And therefore, by measuring this character, angular momentum character, by the Stern-Gerlach apparatus of the silver atom, we are in effect measuring the angular momentum character of a single electron. That was the advantage of doing it with silver. But now we know that had we done it with sodium, it would get the same result because it also has the same character, same property. So we now have to understand the character of this Stern-Gerlach apparatus, and we have to develop a theory for the for whatever we have observed. That's to be theoretical explanation to that. And that's what we'll try to develop using the theory of spin angular momentum. But before I do that, let us illustrate some uh, peculiarities. Even peculiarities can be peculiar in quantum mechanics. Let us illustrate that. We have learned about the Stern-Gerlach apparatus, but now we will will conceive an experiment with a series of Stern-Gerlach apparatuses arranged something like this. I'll just show a picture. Well, here is a picture similar to what we showed in one of the earlier classes of this Stern-Gerlach experiment. So, Stern-Gerlach experiment. Now, here, as you have already learned, there is a magnet with North Pole and South Pole oriented in the Z direction. Z direction is this. A beam of silver atoms is created, and that moves in the Y direction. Through the magnetic field, and the magnetic field is deliberately created in a non-uniform way, and the way to create that is to create a relatively pointy piece of North Pole and a concave piece in the South Pole, so that the magnetic field lines go this way. So there will be a higher B in this part, a lower B in this part, so there will be a gradient of B, and that is what creates a deflection in the silver atoms depending on the component of the angular momentum in the Z direction. So this is the basic experiment, and in that experiment it was found that there are exactly two spots, and this does not really depend on in which direction the North Pole and the South Pole are oriented, because in space there is nothing, no preferential direction. So if we have the poles oriented in the X direction, it will be deflected in the X direction. Let me show a picture like that. Let me delete this. And then see, here we have a picture where the North Pole and South Pole are oriented in the X direction, and in that case, it is as anticipated. The deflection is in the X direction, though there are 2 points created on the screen. This is a glass plate on which the silver atoms deposit and ultimately make a mark, and there are 2 marks in the X direction. So the conclusion is that depending on the direction of the magnetic field, uh, also the magnetic field gradient, the deflection will be in that particular direction. So far, so good. There is no difficulty in understanding, at least up to this part. Now let me show another picture, another arrangement. See here, what I've done is that here we have the beam going, and there is a Stern-Gerlach magnet here, and that Stern-Gerlach magnet is oriented in the Z direction. So here there is a deflection in the Z direction. There are 2 components going, one up, another down. But now we block the down component. We block the down component and allow only the up component to pass. So we expect that that really passes, there the Z component of the angular momentum is oriented in the up direction. And then if there is another Stern-Gerlach apparatus, a north-south pole, exactly placed in the same way with a non-uniform magnetic field, then we see that all the atoms are deflected in the upward direction and it makes just one mark. So there is no point right in the beginning, in the bottom. So it makes one mark. So our conclusion is that all the atoms now have been oriented in the up direction in Z, and therefore they all are deflected in the same way, and ultimately they land at one spot. This also stands to reason. But now, uh, But now we have a situation where we have now we are not showing individual pole pieces, and it is like a box, but the orientation will immediately make it clear that there is a pole piece here, there is a pole piece here, north and south. So it is just a shorthand way of drawing the same arrangement of the Stern-Gerlach magnet. So we have a beam of silver atoms coming through the first Stern-Gerlach apparatus, which makes the orientation in the up direction in Z because the other one has been blocked. But now, instead of placing the second Stern-Gerlach magnet in the Z direction, we place it oriented in the X direction, north-south direction. Now, what will happen? What is observed to happen is that now they will have again two spots of equal intensity and oriented in the X direction. This means that unlike or this means the effect of this Stern-Gerlach magnet is not like a sort of a screen, not like a something that sieves out a part of it. Uh, what it allows to go through are the atoms whose spin direction is oriented up. But now when it passes through a magnet oriented in the X direction, then it makes two spots, means what goes here has two possible directions in the X, two possible orientations in the X direction. So here you have a beam passing which is oriented in the Z direction, but that has components in the X direction, equally strong components, because the two dots have come to be this exactly the same strength. This is also not very difficult to understand. But now, uh, let me show another arrangement. This time, we have oriented it in another direction, not X or Z, the second one. So the first one remains the same. We have a Stern-Gerlach apparatus with the north-south poles oriented in the Z direction. One of the beams is blocked and the other one is allowed to pass through. But this one, the second Stern-Gerlach experiment apparatus, is oriented in an arbitrary theta direction. Now, what will happen? Now, also there will be two spots oriented in the theta direction, but then the intensity of the two spots will be different, will not be the same. And it has been found that if the angle is theta, then the proportion that falls in the upper spot is cos square theta by 2. That fraction is cos square theta by 2, while the fraction that lands in the bottom spot has a fraction sine square theta by 2. So if this were oriented in the x direction, then theta would have been 90 degrees, and 90 degrees means theta by 2 is 45 degrees. So this is 1 by root 2. The square of that is half. So half and half. That is what is expected to happen in the if this Stern-Gerlach magnet were placed in the x direction. That's what has been said in the last slide. So we have learned then, in addition to what we have already learned, that if there are two Stern-Gerlach magnets, the first one is called a preparer because it is preparing the spin in the opposite direction. It is preparing the spin in the opposite direction. And then this beam of silver atoms that goes to the second one, and then it makes two possible dot, means this beam has components in the theta direction, and depending on the strength of each component, we have the probability of a particular silver atom going either up or down. The probability of going up is cos square theta by 2. The probability of going down is or landing at the bottom spot is sine square theta by 2. So this is what we have learned additionally. Notice this is not theta, this is theta by 2. Okay, so this is also something not extremely difficult to understand. So let's proceed. Now we have a situation where we have the same arrangement, but now there are three magnets. The first one, the spin preparer, prepares it in the up direction of Z. The down is blocked. So in the Z direction, it has only the upward spin component. Now it goes through a Stern-Gerlach magnet that is oriented in the X direction. Now after that, the down component of that is also blocked. So first it was the up Z, then it is up X, and now it is again allowed to pass through a Stern-Gerlach magnet which is oriented in the Z direction. What is observed is that still we have two spots. Now, the peculiarity of this situation is that supposing this magnet were not there, that means the atoms that are prepared in the opposite direction are directly allowed to pass to the second magnet, then there will be only one spot. We have seen that already. The lower spot will not be there. But if this second magnet is put, then the lower spot appears. So it is not like sort of screening out some, it is doing something else. It is actually doing something else, and I will come to that little later. But the point here is the peculiarity of the situation is that here we have a spin preparer oriented in the Z direction. Prepared means one part is blocked, the other part is allowed to go through. So it has been prepared in the opposite direction. Second one is preparing is in the up X direction. So this is a preparer. This is also a preparer. But this is an analyzer. So ultimately, this one analyzes the spin components, and it leads us to conclude that it has both the components. Okay, it has both the components. Now, if it is oriented in exactly the X direction, the components are of equal strength. If it is oriented in a particular direction, it will have different strengths depending on the angle. But ultimately, the point is that they have there are two dots. Now, this we need to explain with the help of the theory that we develop. These behavior that we just enumerated using various, I would say, thought experiments, because it is not exactly possible to orient three Stern-Gerlach experiments in this way. So exactly this experiment has not really been done. What has been done is something equivalent to this. But scientists are convinced that if this a theory is built on the basis of this assumption that this will be observed, then it is a reasonable assumption because in various experiments, similar observations have been made. So let us now proceed to develop the theory or spin that will explain these behaviors. Okay, now let's carry on. We now need to develop a theory for these observations that can explain these observations. The way it actually happened was that in 1925, two students, at that time they were students, probably postdocs or maybe just PhD students, Paul Schmidt and Uhlenbeck, they sort of, by analyzing the spectra of hydrogen, they guessed that there should be another additional two-valued angular momentum. And they sort of wrote up a paper, and then they sent the paper to a journal, but at the same time sent the paper to various important scientists. One of them was Lorentz, and Lorentz immediately wrote them back, please don't send this paper because it's nonsense, because this cannot happen. And he actually calculated that if electrons were spinning like that, its surface speed would be greater than speed of light, impossible, and therefore you just abandon this paper. But unfortunately or fortunately, by then, Gauss-Schmidt and Uhlenbeck had already shot off this paper to a journal. So it had reached the journal, and the journal published it. And that's how this paper actually got published, and we came to know about the spin. Independently, Pauli was working on various things, and he had guessed this kind of effect might be there. But he, due to the same reason that Lorentz objected to the idea of spin, due to the same reason, he had also calculated surface speed, and he also concluded that it cannot happen. So he did not publish it. But he had written about this strange non-classical two-valuedness of quantum things. So he had a clear idea that there are some non-classical two-valuedness. And now we know there have been various experiments by which the existence of spin has been clearly experimentally verified. So we have now a clear idea of what spins are. So I would not say that. I would say that we have a clear idea what the effect of spin is, but it is basically assumed to be some intrinsic angular momentum. Even if an electron is static at one place, it has an angular momentum of either plus h cross or minus h cross by 2 in any direction. So now we have to develop a theory for it, and we will do that using the same theoretical structure that you have used earlier. Earlier means using the Dirac notation. And there we have said that, okay, we note that there is a state after the silver beam has passed through the first Stern-Gerlach apparatus, and you block off the lower one, it is oriented in the plus h cross by 2 direction, so that if you place another Stern-Gerlach in the same direction, everything goes in the top, nothing goes in the bottom. So there is a state which is completely oriented in the up direction in z, and if it is in that direction, then with probability 1, all the atoms have a spin angular momentum plus h cross by 2. Therefore, we can conclude that specific state of the atoms is an eigenvector, because when again it is applied on by the same operator, what comes out is in the same direction. Therefore, we conclude that let us use the simple notation. In different books, you will find different notations. Let us use the simple notation that if it is oriented up, we'll say up, and in the z direction. This is the ket. If a silver atom is this in this state, then with probability 1, it will have an eigenvalue plus h cross by 2. So uh, for this state, the eigenvalue is and similarly there will be another similar state. If it is prepared in this state, then with probability 1, all the atoms will fall in the lower dot. The eigenvalue is minus h cross by 2. Now these are the eigen vectors, and these eigenvectors have the property that if it is in this state, it has no component in this state. That means there's no silver atom falls in the lower dot. If it is in this state, there's no component in this state. That means no silver atom falls in the upper dot. And therefore, these two can be assumed to be mutually orthogonal. So in our mind's eye, we will assume them to be something like this. Two vectors, this is up z and this is down z. And if it is like this, then any vector, any spin state A can be decomposed as a linear combination of these two basis states. If these are two eigenvectors, they can be thought as basis. By the way, in this spin space, there are only two dimensions, and therefore only two of the bases suffice in representing any. We have already done situations where infinite number of bases are necessary, but in this case it is far simpler, only two. So any given A spin state A can be decomposed as components along these two directions, and therefore A can be written as some A1 up plus A2 down. And A1 and A2 are in general complex numbers with the property that these are complex numbers with the property that A1 square plus A2 square should be equal to 1. Okay, because the silver atom either falls at the top or falls at the bottom. A1 square is the probability of it going to the top. A2 is the probability that mod A2 square is the probability of it going to the bottom, and these two added together must give 1. Okay, so we have defined the basis in this spin space, and these are the two basis vectors, and accordingly every vector can be in any spin state can be visualized as a vector, and that can be decomposed in these two directions like this. Now the question is, how do we take inner product? Because we have already learned what inner product is in the Hilbert space. This is not a Hilbert space, this is a separate space, spin space. And in this space also we'll need to define inner products. So suppose A is defined like this, and there's another vector B, which is defined as B1 up and B2 down. And again, B1 square plus B2 square is equal to 1. That's obvious. But now we are trying to figure out what is this. What is in the same way that we have done. First, we have to take the bra of A, which you now know how to do that. We will have to take the brass of this and we have to uh, take the conjugate of these coefficients. Okay, so this one will be A1 star, the bra of the up Z, plus A2 star, the bra of the down Z, this, and then we put the B, it is B1 up Z and B2 down Z. And if you take a if you simply multiply, then you get A1 star B1 up Z plus A1 star B2 up Z down Z plus A2 star B1 down up plus A2 star B2 down. All right. Now you will get the correct result of the dot product A1 star B1 plus A2 star B2 if these are true. Sorry. If up Z with up equal to down Z with down Z equal to 1. Up Z and down Z. And if it is up Z down Z equal to down Z up Z equal to 0. Then these two cancel off and you are left with only A1 star B1, exactly the rule of the dot product. Right. So we have to assume in tune with what we have just drawn that up Z, if you do that, that leads to 1, and that essentially means that these have to be normalized and they are orthogonal. This implies that these are orthogonal. So we additionally need to ensure that these basis vectors are normalized. And if any vector is not normalized, all you need to do is to divide its magnitude by the square root of this. Similarly, if you have, let me delete some part. So if you have a vector A and if you take its dot product with itself, then it is clear that it is A1 star A1 plus A2 star A2 is equal to obviously A1 mod square. A2 should be equal to 1, and this is if you do not get 1, then what has to be done is that A has to be divided by square root of this. It's easy. So you have to divide by square root of you have to divide it by this in order to make it normalized. That's not a very difficult thing to figure out. One thing you have to understand that sometimes students make mistake in that due to some strange reason. I don't really understand how, but I have seen people making mistakes. That two spin vectors that look different might be the same. For example, if you have a spin vector, say A, and if you multiply that by say I, then it is the same vector. It does not really change. Because if you take it like this, it will simply disappear. For example, if say A uh, is 1 by root 2, I have to normalize it, 1 by root 2, it is say up z plus I down z. Another vector is 1 by root 2, it is minus I up z plus down z. Then these two apparently look different, but they are actually the same. Why? Because if you multiply this one by minus I, you get exactly this. So therefore, you have to be careful about what distinguishes two vectors. The vector is actually in the same direction. One is multiplied by a constant minus I. So they represent the same vector. Okay, now what I was doing is actually rather simple stuff. So let us get away from that. By the way, the ones that we did earlier uh, that are more complicated than working with spins, because spin has only two dimensions, and therefore every mathematics that we do in spins will be far more simple. So it's not difficult at all. For example, this vector, if you want to represent as a column vector, how do you represent? Simple. Your sorry, your up z will simply be 1 0, and down z should simply be 0 1. Simple. So this is not difficult at all. And if you consider any arbitrary spin vector A, then that can be represented as a linear combination of these two. So it is A1 1 0 plus A2 0 1. As simple as that. And this is actually equal to A1 A2. This kind of column vectors representing a specific spin state is sometimes called spinor. So when we use the term spinor, you just know that it is a column vector representation of a any given spin vector A. And then if another vector is given as B, that will be say in the same way B1, B2. Then how do you write AB? You simply take the bra of this, which will be A1 star, A2 star, and this one is B1, B2 is equal to A1 star, B1 plus A2 star. That's simple. Therefore, working with the bras and kets in the spin space is not difficult at all. Is this clear? It is very simple stuff actually. So we first have to take you have to take the A as the spinor, convert it into its corresponding bra by making it as a row vector with conjugated terms, and then just product it with the B. We can give a simple example to illustrate that. We need this also. Yeah. Just to illustrate how these things are done. Suppose there is a vector C given by 1 and I, and vector d dl2 is equal to I1, then your C, we first have to normalize it. C is, it is 1 minus I, because you have to take the conjugate, and it is 1 I. This is equal to 1 plus 1 is equal to 2, and therefore normalization C will be normalized C 1 by root 2 of this 1 I. And D is similarly 1 by root 2. In the similar way, you find the same thing. So it is I1. And your C, D is 1 by root 2, 1 by root 2 half. It is, you have to take this conjugate, 1 minus I, and this one is I1 is equal to half. It is 0. So these two are actually orthogonal vectors. So you conclude that these are orthonormal vectors. These two vectors are orthonormal vectors. Okay, let's continue. You can easily see that this mathematics is far simpler than what we are doing so far. And that's why many books you will find start with spin and go into other things. Now, as you have seen, the matter of spin, its mathematics is simpler, but the concept is a bit difficult to grasp because students often come out with somewhat a concept like the first Stern-Gerlach apparatus is acting like a filter. So if everything is oriented up, then if I have another filter that will look for its component in the x direction, then nothing should come because everything is oriented up. No. If everything is oriented up, still there will be components in the x direction, plus x and minus x. It will be in plus x and minus x directions. So that is something that we have to understand. And most importantly, when we place two Stern-Gerlach apparatus in series, then the fact that the second Stern-Gerlach apparatus erases the information created by the first Stern-Gerlach apparatus. This is another very important information that we have to understand and use. It essentially means that they are the corresponding operators are non-commutative. Any question?
Sir?
Yeah.
So, when you taught the spin for the first time, you actually told that the Stern-Gerlach experiment,
Yeah.
that we should get the straight lines on the screen, but why do we get curves? You told the reason about that. Can you tell that again?
Yeah. Yes. Actually, you see, you're supposed to see if the spin were not there. The spin idea were not there, then you are supposed to see, in this case, a smudge of dots in this z direction, because there will be all possible orientations of the electrons in various directions. What we actually see are these. Supposed to see are these, but you actually do not see this. The reason is that in this case you are assuming that all the silver atoms are in a very narrow beam without any spread in the x direction, but actually there will be some spread in the x direction. Now, if you have some spread in the x direction, then the electrons that are the silver atoms that are in this part and in this part, they will see a slightly different magnetic field. The magnetic field was actually maximal here, but as you go away from that particular point, the magnetic field will be slightly weakened, and as a result, they will be deflected less. So they will be deflected like this. They will be deflected like this. And here they will be deflected like that. And so actually what we'll see is something like this. Because there will be, it's extremely difficult to make it like a pencil-like narrow beam. You will see it has some spread in the x direction, and that x direction spread, the ones that are at the ends, will not see much of gradient of B. Because the shape of the pole pieces were something like this. So if there are here, in this part, there will be a lot of difference, all right. But as you go towards the end, you will find more or less they are coming like this, and therefore they will not see very much difference in the. They will not see a good value of del B del X del Z. So therefore they will be deflected less. Okay, at the center they will be deflected maximally, but at the edges they will be deflected less. But this experiment has been conducted with very little spread in the x direction, and then you do see something like this. So this is actually true. When Stern and Gerlach did it for the first time, at that time they saw something like this, lip-like structure. Is it clear? Now we have to end because there's no time. We'll continue in the next class. If there's any question, we'll take it up.